Welcome to lecture 17. In this lecture, we discuss basics about localization. And this is a topic that we will come to again and again. So we'll see as and when we need, we will discuss this as much as possible. So what exactly do we mean? So definition. A subset U of R is a ring, is multiplicatively closed if 1 is inside U and for all U prime in U, the product U prime is inside U. Okay. So for example, the non-zero elements in a domain, for example, the non-zero integers in a domain, 2. This is a little bit special case of the second one, R minus P, where P is a prime ideal. By definition of P being a prime ideal, it is clear that if U and U prime are not in P, the product is not in P, okay? And 1 is definitely not in P. Okay. And third example, so really we are, the second one is the first one is an example of the second one, but there is a new example. So let A be in R not nilpotent. In other words, no power of A is, that is, there does not exist M such that AM is 0. Okay. Then the set 1, A square, and so on is multiplicatively closed. Okay. So this is what we mean. These are examples of what we mean by a multiplicatively closed set. There might be others also. For example, you could take a union of two prime ideals and then take the complement and so on. Okay. So definition. By U inverse R, okay, or sometimes R adjoint U inverse, or sometimes R sub U, U is multiplicatively closed. U is maybe I should just erase this whole thing and rewrite it. Okay. Let U inside R be multiplicatively closed set. Okay. By U inverse R or R adjoint U inverse or R sub U, various notational convention used by various authors. Okay. We mean the set. So these are pairs of elements from R and in U such that R is in R, U is in U, not okay, under an equivalence relation. So equivalence classes under this equivalence relation where this is the equivalence relation RU is equivalent to R prime U prime if there exists some U tilde in U such that, okay, U tilde times R U prime minus R prime U equals 0. Okay. We denote the equivalence class of R equivalence class of RU by the fraction R over U. Okay. So really we are saying, we are thinking about fractions, but of course as in Q, 1 over 2 same as 2 over 4, so it's really there. Okay. So this is really that statement. How do we identify two fractions? And if you are working over a in general, not just rationals, one needs to put this as the definition. Okay. Okay. So one defines such a set, and few okay, so for example, Q is Z, U inverse Z, where U is Z minus 0. Okay. Or the rational function field in one variable is U inverse the polynomial in one variable. So this is rational function field in one variable, polynomial in one variable, where U is all the non-zero polynomials. Okay. So it is these constructions that actually that construction U inverse R generalizes. Okay. So what is so just a little bit of notation. Okay. If U is the complement of a prime ideal, okay, then U inverse R is typically written as R localized at P. I mean, this is called R localized at P with subscript P. Okay, 1. And 2, if U is 1, A square, and so on, A not nilpotent, then U inverse R is typically written as R sub A, or sometimes R adjoint 1 over A. Okay. So this is just variations of the notation that one would keep using or comes across. Okay. So this is just okay. But why are we studying this? U inverse R is a ring. Please check. Okay. Sorry, maybe one should just say check. Sorry, this you should check. Not very difficult at all. Okay. How, I mean, as how one should add fractions. Okay, just keep, that's all that you have to keep in mind. Okay, and R2, U inverse R, in which a ring element goes to the fraction R over 1, is a ring map. Okay. Okay. So Z to Q is injective, K adjoint X to K round brackets X is injective, but in general it need not have such properties, so it is injective. What property does this ring have? Okay, proposition. Every ideal of U inverse R is an extended ideal. Okay. In other words, that is, whenever if J is an ideal here, then there is an ideal in R, extended ideal from R. Okay. There is an ideal in R whose extension gives J. Okay. But okay, this might sound like a curiosity, but it has an important application. We will prove the proposition. Just this is the first time we are coming across this notion of working with fractions, etc. I will do it so that we become familiar with that. So it has an important application if R is Noetherian. U inverse R is Noetherian. That's because everything is an extended ideal. So whatever generating set generates it in I will generate it as in U inverse R also, but it's a finite generating set here, so that's finite generating set there. Okay. So, so this is what this is so this corollary is important. So now let's prove the proposition. Okay. So let J be an ideal of U inverse R. Okay. Let take a generating set for it. Let G inside J be a generating set. Okay. So just we keep saying generating set. There is no significance to that statement. There is no substantial significance to that statement of this proof. J itself is a generating set for J. So one could have just taken J itself. Okay. But all I want to say is that the argument works for every generating set. Okay. Now let G1 be the set R in R such that there exists U in U such that R over U is inside G. Okay. So these are the numerators that appear in the fractions inside G1. Okay. Let I be the R ideal generated by G1. Okay. The claim is that J is the extension of I. Okay. Let's write that. So notice that if you, for every R over U inside G, R over U is inside, can be written as R times 1 over U. So this is an element inside G1. Okay. And this is an element in U inverse R. Okay. So in other words, G1 generates the same ideal as G, that is G1 generates the same ideal as G in U inverse R in the after localization. Okay. G does not belong to R, so this statement makes sense only in U inverse R, and from then we can conclude that I extended, so this now implies that, so in particular I also will generate I extended to U inverse R is J. Okay. Notice that I itself is a subset of J, therefore if you extend I to U inverse R, it is going to be a sub-ideal of J. But already the subset G1 generates J, so therefore I also generates J. Okay. So this is what we need in this proof. Okay. So this is the proof. So every ideal is an extended ideal. Okay. So just again one more piece of notation. We will write U inverse I for I extended to U inverse R, and later we will see also for modules. So this is okay. Okay. So here is some important proposition. I mean, basic properties of this, which we keep using all the time. Okay. So U and R as above. 1. For any R ideal I, U inverse of I is U inverse of R if and only if U intersects I, non-trivially. Okay? And the reason is, if this is true, so you should write out the details. If this is true, then there will be some element inside I, and 1 over that will also be inside this ring. So some A divided by A, that will give 1. Okay, so that's what one will have to check. Okay, so this is U inverse I becomes a full ring only if and only if U intersects the multiplicatively closed set, that if and only if I intersects the multiplicatively closed set that that was inverted. Okay. 2. If P is a let P be inside P inside R be a maximal, be a prime ideal, okay, such that P does not intersect U. Okay. So P, U inverse P is not going to be the whole ring. Then P inverse, U inverse P is a prime ideal of U inverse R. Okay, so this is what we have. 3. Conversely, if Q is a prime ideal of U inverse R, then we can look at the contraction of Q to R, which is a prime ideal of R, and then we can extend it to U inverse R. So we get this one. This is then Q. Okay. And so these are statements that can be proved relatively without difficulty. So proof is left as an exercise. Okay. So the point that one gets from these is the following. Okay. So recall that what we called the prime spectrum of R is a set of prime ideals in R, P a prime ideal of R. Okay. This we you did this in the exercises, which we denote by spec R. Okay. Now, what does this result say? The previous proposition say? It says that spec of U inverse R to spec. So the previous proposition says there exists an injective map to spec R. Okay. And the map here is, if you have a Q here, Q goes to Q contracted to R, and that is a prime ideal here. And no, from the last part, if Q and Q prime are different, then the target will also be different. That's what the last part will say. Okay. So this is injective. So this is one application. Right. So this sort of observations have to do with giving a topology on the set spec R, which we will do soon, but that's where this sort of discussion goes to. Okay. Okay, so just now we can talk about localizing modules. We can similarly define U inverse M for an R module M. Okay. U inverse M, the set of all MU where M is in M, U is in U, modulo an equivalence relation where M1 U1 is equivalent to M2 U2 if there exists some U3 so in U such that U3 times u2 m1 minus u1 m2 equals 0. So again, it says that two fractions are same, and we check this by cross multiplying the denominators. So that's the that's the idea behind this, to work in to make it work in all generality, not just with rational numbers or q. One needs to also put this inside here. Okay, so this is a U inverse M is a U inverse R module, okay. And yeah, so let f from M to N be an R linear map of R modules. Okay, this gives an U inverse R linear map which we will define like a fraction f over 1 from U inverse M to U inverse N. What is the map? So here are elements of the form x over u, and this gets mapped to f of x over same u. Okay. So this is a U inverse R linear, and so any such f gives such a map. Okay. So one more definition in this context. A ring is said to be a local ring if it has a unique maximal ideal. Okay. For example, if you, so let's look at the example that we saw. Okay. Let U be R minus P, where P is a prime ideal. Okay. Of course, fields are local rings, but again, that's not. If this were the only local rings, this notion may not be of much use. Okay, so there are other things. So P is a maximal ideal. Now, what are the prime ideals of R localized at P? So the earlier proposition, which in part we proved and in part we didn't prove, gives the following, which is that they're exactly those of the form Q extended to R localized at P, where Q does not intersect the multiplicatively closed set. Okay, and this condition is just the same thing as Q is inside P. Okay, so this is what that proposition said, that the prime ideals that don't become the whole ring after localizing are exactly the prime ideals that don't intersect the multiplicative closed set, and when you extend those things you will get prime ideals, and these are the only prime ideals of the localized ring of R inverse U. Okay, so these are exactly these form. So hence the extension of P to Rp is the unique maximal ideal of R localized at P. Okay, so this is the example. This is an example of and this is an example of a local ring. Okay, there are other local rings also which doesn't come out as localizations like this immediately. Another example, and this is very closely related to polynomial rings in a way. So first of all, notice that polynomial rings are rare. If there's more than one variable, I mean there's at least one variable, it is not going to be a local ring, because every irreducible you could take an irreducible polynomial let me just explain it, sorry. Okay, so let me just say non-example. Okay. K adjoint X is not local. Okay, why? For every non-zero f, I mean every irreducible f of x in kx, the ideal generated by f of x is maximal. And there are infinitely many irreducible polynomials. Okay. So therefore, there are enough. So this is not one of the things that you have become familiar with in the course of these lectures is actually not local. Okay. But an example. By k double brackets x, in fact one can do it for more variables, but just to get familiar, let's do one. We mean the ring of what is called formal power series over k. Okay, so let's again put k to be a field. Okay. So what are these? This is just elements of k are of the form ai x to the I inside n. Sorry, it's not a sum, it is just, okay. So this is just a0 plus a1 x plus a2 x squared and so on, and no statement like, so unlike for a polynomial, for this to be a polynomial, it has to be 0 after a while. In finitely many stages, it has to become 0. Here, there are no such conditions. Okay, and then one can check that a0 plus a1x plus this element is a unit if and only if a0 is not 0. Okay. So that's one statement one can check. Okay. The ideal generated by x is maximal. Okay. And every ideal, every proper ideal of K power series ring X is inside this. Okay. So this is a local ring. Okay. And so various algorithms that one can work in polynomial ring can also be extended to such power series rings, but that's not something that we will pursue at all in this course. Okay. So just one piece of notation before we finish. Okay. When we say we say Rm is a local ring to say that R is a local ring with maximal ideal, with unique maximal ideal M. Okay. So that's the end of this lecture, and in the next lecture we will look at what is called determinantal trick and Nakayama's lemma, and then we will try to understand some idea of the topological aspects of spec R.